Okay, there's a bunch more to say about waves. There's a lot in the book that treats this subject pretty well and pretty thoroughly, but I want to talk about it because I love to. Anyway, we were talking about a couple of kinds of waves, transverse and longitudinal, and I wanted to give a couple of examples of like trying to figure out which ones are what. Like waves in the water, transverse or longitudinal, ocean waves. You see these waves like that, and they're traveling this way. That's the direction of propagation. Which way is the water getting displaced? Obviously, at least some of it is up and down. That would be transverse. Uh, but actually, if you look real closely, a little fish in the water probably is going on a little kind of a circly, ellipsy thing. And so actually, there's a little bit of back and forth. So it's kind of interesting. Maybe water waves are a bit of a mix of transverse and longitudinal. What about sound waves? The kind that you're using to hear me right now, except for the radio waves that are probably transmitting something somewhere for you. But anyway, the sound waves that are getting from me to that computer right there, and the ones that are getting from your speakers to your ears, are in the air. What is air? A bunch of molecules, a bunch of individual molecules. So what kind of wave, transverse, longitudinal, torsional, whatever, would propagate through a bunch of air molecules? How would you even approach that? How would you know? Well, you have to think about mechanically what happens. These molecules have to hit each other. And all I can figure is, here comes my vocal cord or whatever, and it slaps these molecules and knocks them in this direction, and then they go hit other ones, and they bounce back, and those ones go knock something else. So you get these waves of compressed zones of more crowdedness and rarefaction there, and they propagate. But think about what the molecules are kind of doing. It's kind of push-pull. So they're pretty much longitudinal. Earthquake waves are complex. When there's an earthquake, as your book talks about a little bit, different kinds of waves happen. Some of the waves travel along the surface and are sort of transverse. Others are push-pull through the planet, and some travel through liquids and some don't, and you end up getting all kind of amazing information. If we had class, I would tell you so much about a friend of mine who used to use jumping trucks to shake the earth and look for oil. He even let me take a piece of paper worth about a couple $1,000,000 to school to show my students. Probably have to kill me if I lost it or something. Showed where oil was because the jumping trucks sent waves into the ground, and the waves echoed back up off different types of strata down there 4 to 8 miles under the earth. It's kind of a sonogram of the earth. Oh, there's so much we could talk about with that. I'll leave that for now. But again, different kinds of materials sustain the propagation of different kinds of waves, transverse, longitudinal, torsional, whatever. Now, I started talking in class. Didn't say it in the last video, but not really in the last video, but I started talking about a thing called interference and superposition. Since you heard it in class, I can say it pretty quickly, but I do want to write the words because I got all kind of applications of this stuff. Okay, first of all, we have the thing called the superposition principle. Superposition just means you add. If two waves are in the same place at the same time, you just add what they were each going to do individually. Once that wave says go up 4 feet, the other wave says, no, go down 3 feet. 4 plus -3, 1. You go up 1 foot. That's a simple idea. In fact, it's one of the simplest ideas you ever encounter in this course. You got two things. Want to know what happens? Add them. But it leads to all kind of interesting effects that are very much worth talking about. And in general, I want to make sure you got two terms down, and I said them in class. There are two kinds of interference. There's constructive interference, when the superposition of two waves makes more of the same, when they agree on which way to go, when your mom and your dad both tell you to take the garbage out back. And then there's destructive interference, where your mom says take the garbage out back, your dad says take the garbage out front. You don't know what to do, so it adds up to like nothing or not much. So these are two examples of superposition. Sometimes waves get in the same place at the same time. They make more of what each of them is trying to do. Other times they argue over it. Have a slight quibble that I always like to point out. I could just shut up about it, but it just bugs me a little bit. The word interference can be misleading because it sounds as if the waves are doing something to each other. They are not. Think about your mom and your dad telling you to take the garbage out. Your mom says take the garbage out back. Your dad says take the garbage out front. They're sort of interfering with each other, but it doesn't mean they're having a fight. Maybe they don't care. It's all your problem, right? This is what I'm saying about two waves that interfere. If like, here's a pulse and here's another pulse and they're going by and they argue over what to do with the medium at the point where they're at the same place at the same time, that doesn't mean they're mad at each other and they don't destroy each other just because it's destructive interference. It's just that they follow each other's plans. They go on quite right through each other very healthily. So know that about constructive and destructive interference. The waves themselves are not doing anything to each other. They're just agreeing or disagreeing over what to do with the medium, and that's the medium's problem. Maybe you get the point there. So I want to tell that there's a few different examples of standing waves that are particularly interesting, and I want to focus on one that we've already seen and already said some of the words. I talked about a thing called standing waves. Standing waves doesn't mean, you stand here and wave. You might have figured that. Standing waves are waves that look like they're standing there, kind of, sort of. I mean, it's not that you don't see any motion, but you don't see the propagation of the wave, and there's a very good reason for that. I'm going to, and I'm not going to ask my wife to get out to hold the spring again because you've already seen this, but I will draw stuff for you. So hopefully you'll get this. I'm about to talk about, and I'll even be all good and put the word up at the top, standing waves. Standing waves. Okay, imagine this. What if I had, I think I'm going to use different colors. That's what I'm going to do, yeah. Okay, what I'm going to say here is what if I had a wave that looks like that going this way through a medium? You can picture water waves, perhaps. There may be waves on the spring since you've seen that. But what if there was also this blue wave and they just happen to be in the same place at the same time, but there's a complication. The blue wave is moving the other way. So if the blue wave has the same wavelength, they got the same wavelength, blue and red have the same wavelength, let's have them travel at the same speed, but they're traveling past each other. What does this do to the medium? Well, here's the sort of medium position of the medium, the equilibrium position right there. That's the average place. We just add, and I'm going to go through and sort of painstakingly, I won't take too long, I'll carefully show you what the sum of the two waves looks like at this instant. At this instant, well, this is 0. Let's say this is 1 and this is -1. At this instant, we have 1 for the red and 1 for the blue makes 2. So 2, I'll plot it. We had 0 here, we have 2 here. 0 plus 0 is 0. -1 plus -1 is -2. 0 plus 0 is 0. +2, 0, -2, 0, +2. These two waves just make more of the same shape. You see, it's got the same wavelength, but at the moment, that's what the spring looks like at this moment. Now what I'm going to do is, and this makes for a slightly messy picture, I wish it was bigger looking for you, but let me draw the red wave having done a little bit of its moving to the right and the blue wave having done a little bit of its moving to the left. So here's the red wave a little later. Now I'm using dashed lines this time. There's the red wave a little later. I'm going to draw the blue wave a little later. Remember, they're going in opposite directions. That's not bad. And now I'm going to add them. It's getting a little hard to look at, but we'll try. So now, at this point here, I've got about a half plus a half makes about 1. Here, I have about positive, I don't know, maybe 3/4 or something, plus -3/4 add up to 0. That's interesting. That's what I got last time. That place was 0 before. And then I've got like about -1/2 plus -1/2 makes about -1. Then I got about +3/4 and -3/4, I don't know, something like that makes 0. I'm just going to go through and add these waves all the way through, and look what I get. Maybe you can see this. I get a sort of slightly miniaturized version of the one I got before. But it's in the same place. It's like you see this wave, and instead of moving this way or moving this way, because you can't see the individual waves that are getting superposed, you're just seeing their sum. That's the only thing that's visible. The medium is doing the sum of the two things. And what this sum is doing depends on where you are. If you are right here, or right here, or right here, or right here, or right here, it ain't doing a dadgum thing. It's not going anywhere. It's just frozen there. Whereas this part is going up and down, and I won't belabor my picture too much. It's already messy enough as it is. But picture as the red wave continues to move this way and the blue wave continues to move this way, there's going to come a time when they are flat out opposite each other and are interfering completely destructively. At that instant, you'll have no displacement here, or here, or here, or here, and still isn't any there, and the thing would be flat all the way across. But I won't stop there, because a little bit later, they're now further past, and now it looks like this. It's going to be a good drawing. I'm proud of this. It's going to look like that. And then it's going to look like this. It's kind of aesthetically pleasing. And then it's going to go back through the same thing. So you won't see it travel to the right. You won't see it travel to the left. All you'll see is this sort of pulsating thing just standing there with, I mean, I'm going to try to do it here. It's like, it's not like, look at it go, or look at it go. It's like, look at that thing stand there and just sort of throb. You got its places going up and down like that. You might even picture a bunch of people. I just thought of this. Just now I thought of this. What if you had a whole bunch of people standing in a line, and you like arranged for alternate people to jump up while other people squat down? And so you see this, and you don't see anybody go anywhere. That's what it looks like. And you saw it. You can go back and look at the video where we were holding that spring, and you can see these things. I called them different harmonics. I used adjectives. I'd say, like, look, a third harmonic, transverse standing, vertically polarized maybe, transverse standing wave. I said all that stuff. And you saw it, and there's these different harmonics. We're going to talk about that. The thing is, I just presumed that this exists because of and consists of two identical looking waves with the same amplitude and the same wavelengths traveling in opposite directions in the same medium at the same time. You might say, what are the chances of that? You know, if I really trained my wife up on this really good, I could have maybe taught her to send me waves that look just like the ones I sent her, but that'd be hard. Instead, I just told her to hold tight. So what were these waves traveling the other way? They were the reflections of the ones I was sending. I was sending waves down, and they were bouncing off her hand and coming back. They were flipped over upside down, which is okay. But they were identical looking waves. A wave in its own reflection looked the same, basically, at the same wavelength, same amplitude. And as they pass through each other in that same medium at the same time, you can't see either one on its own. You see their superposition doing this weird throbby stuff. I hope that got across to you. It's a little bit hard to visualize in a way, but again, a standing wave is the superposition of a wave and its own reflection traveling in opposite directions, the same medium at the same time. And it happens very, very naturally. Okay, so let's see here. How many ways can this happen? Well, one thing that can happen is you can have, you know what? I'm going to erase my messy picture at the top. I'm going to erase my messy picture at the top and just draw the possibilities. How many are there? Lots. Here's some things that can happen. Here's one person holding one end. Here's a person holding the other end. What's the simplest kind of standing wave you can have? It can look like jump rope. Now, I don't mean necessarily jump rope. That is a first harmonic. Oh, said it. A first harmonic standing wave when you do the circularly polarized. But since it's hard to draw the circles in and out of the board here, let's not do circularly polarized. Let's do vertically polarized transverse waves. So this is doing this. I'm not even trying to do that. keeping it simple, just straight up and down like that. That is called the first harmonic. The first harmonic standing wave is one that has fixed ends and a whole lot of action going on in the middle. And there's names for these places, these fixed ends or action in the middle places. One of them here, this is called a node. This is also called a node. You can look at it this way. A node is where nothing happens. Nothing happens at a node because what kind of interference is always there? Destructive. This, of course, being the opposite of a node, is called an antinode. Antinode. Opposite of a node. It's where crazy stuff's happening. All kind of stuff's going on in an antinode. Every time in an antinode, every time one wave says go up, the other one says, yeah, go up. So what do? You go up a lot. And then the first wave says, change my mind. Go down. And the second one says, I changed my mind too. Go down. Imagine if your parents jerked you around like this. What if your mom and your dad both said to take the trash out back, and before you could even get out there, they said, no, take it out front. They both said it. You'd be going crazy, right? But what if they kept changing their minds, but one says out front, one says out back? Then you stand there like a deer in the headlights, no, and not have any idea what to do. That's what happens at a node. But again, this is the first harmonic. Let me draw the second harmonic. Here comes the second harmonic. There's the second harmonic. It's kind of like, with this one, here's a node, but there's another node. There's another place where no thing is happening in the middle. And there are two antinodes. These are antinodes, A-N for antinode, and these are nodes. Now, how many nodes does it have? I guess 3, including the ends. Sometimes you might say, like, well, of course there's ends. Like, why count them? Well, you probably should count them. But anyway, I'm going to just count the antinodes of these things. This is, of course, called the second harmonic. Now, I could, of course, go to the third harmonic. And the third harmonic looks like, oh, I messed up. I could do better than that. I've done this on my whole life. There you go. There's the third harmonic. Now, these things can all happen on the same spring. They can all happen on the same spring of the same length. But they do have different wavelengths, and they're going to have different frequencies, too. There's the third. I'll do one more. Here's the fourth harmonic. I could do like, yeah, it's not my best. That's okay. It's okay. Look, it's got 4 antinodes, so it's the fourth harmonic. Now, I want to also talk about the wavelength of these things. Spell harmonic. Got it. What about the wavelength? First of all, let me say that the length of the spring is called L. That's just a nice generic name for the length of the spring, L. And what is the wavelength of this harmonic? Oh, I wish I could. Oh, I can make you guess because I'm probably going to show the video for you at some point and make you guess. So, what is the wavelength in terms of L of the first harmonic? And we're back, and the answer is 2L, because this is not a whole wavelength. Ever drawn in a math class a whole wavelength? It's got to go up and down and back up again. So this is only half a wavelength. So this thing has a wavelength of 2L. And what do you think the wavelength of this one is? That is the wavelength. You're looking at it. It's L. And what about this one? A little bit harder. This is a wavelength, and this is L. L's got 3 parts, and the wavelength takes up 2 of them. So that would make the lambda 2/3 L, And this one, you could say 2/4. You might prefer to just say half. Look, wavelength's half the length. So you might say lambda equals half L. There, we got the wavelengths of the first 4 harmonics of some standing wave, whatever those are. Maybe I'll be able to show you some more. Well, you've seen some, but maybe you'll see more. Now, I can be more generic about this, about what these, I could say that the number of the harmonic is N, like for number, because it starts with N. So anyway, this could be the first harmonic. This could be the second, or the wavelength of the second harmonic, wavelength of the third and the fourth. I wonder if you could come up with a generalized formula for the wavelength of the nth harmonic? I guess I'll let you think for a second. That's a good long second. How about 2L over N? Because if I put a 1 in there, it's just 2L, and that's what I had anyway, right? And how about down here? How about this is 2L over 2? See, the N is 1 there, and here N is 2. 2L over 2 is L. Yep, that is a length. That's a wavelength right there. Yep. Oh, and of course, 2/3 L is 2L over 3. And then this is 2L over 4, isn't it? 2L over 4. So yeah, I guess we got a formula. We're not going to have a whole lot of bad math in this. But you might like to know this. You might like to know, or just figure out from the picture, that the wavelength of the nth harmonic is 2L over N. Yeah. Now, remember we derived something about the speed, and we derived it. Oh, we didn't derive it. We just said it was too easy to derive. The speed of a wave is how far it travels divided by how long it took to travel that far. How far does a wave travel? Well, it depends on how long it is. How about in one period? In one period, a whole wavelength comes by. So it's obviously lambda over t, the distance over the time. You can also write this as f times lambda because f is the reciprocal of t. So we got v equals f lambda. And I'd be interested to see if there's anything I can say about the frequency of the nth harmonic. Let's see, the frequency would be v over lambda, right? See? And v is v, and lambda is 2L over n. But the n is in the denominator of the denominator of the denominator, so it can come up in the numerator. And if I'm talking too fast, the beauty of this is you can play it again, right? Regardless of whether or not your name is Sam. That's a bad joke, okay. Never told that before. Anyway, you get NV over 2L. V and L are fixed. Apparently, we've just found that the frequency of a harmonic is proportional to the number. That is that the second harmonic has exactly twice the frequency of the first, and the third harmonic has exactly 3 times the frequency of the first, and so forth. So that's a fairly simple concept, I think. I'm going to do a quick problem here. This is the kind of thing where I do a problem, I teach you how to do the problem, and then you got to do one of your own for homework. So here's where you really key in and tune in, right? Okay, I'm going to just say 2 people, I usually give them stupid names like Nedbert and Felda or something like that. I don't know, whatever their names are. 2 people are holding a spring. Here they are. That would be Nedbert. And he's holding the spring, and over here is Felda or whatever the name is. Is that a name? I usually draw better than that, but that will have to do. Look what they're doing. They're making a wave. What wave are they going to make? I'm going to make them make this wave. Yeah, that's a good wave. And what I do in these kind of problems is I tell you things like I tell you the length of it, and I'm going to say it's 12 meters. Well, that's pretty long. I'll go with it. It's a long spring. The spring is 12 meters long, or maybe they're big people. So the spring is 12 meters long. And I just tell you something, like I tell you that they're shaking it. They shake it. Let's see, how about, I might say 30 times in 20 seconds. I just made that up because I make up my own problems, you know. So they shake it 30 times in 20 seconds. And then what I do is I ask all kinds of questions. Here's the kind of questions I ask. I'm training you to do a problem, okay? So I'd say like, what is the number of the harmonic? This is a gimme. I hope you know. Well, you just count antinodes. 3. The number of the harmonic is 3. Then maybe I say, what is the frequency? I practically gave you that. Frequency is number of cycles per second. I told you how many cycles in 20 seconds. So I guess 30 over 20. Yep, it's 30 over 20. It's 1.5. 1.5 what? What are of these units. We learned them barely before when we talked about circular motion, named after a guy that sounds like a rental car company. Hertz. Hertz. Not painful, but Hertz. Sorry. Any case, so 1.5 hertz there is the frequency. What about the period? Well, the period's 1 over the frequency, so all that is you flip it over. 1 over 1.5 or 20 over 30, 0.667 seconds. It takes 0.667 seconds for that to happen. Okay, that's nice. That was easy. What if I ask for the wavelength? I just taught you that, the 2L over N thing, or you just eyeball it. Look at this. It's 12 meters long, and this is a wavelength out to there. To, from that, finished it right there. That's a wavelength. It's clearly 2/3 of 12. So the wavelength is 2/3 of 12, which is 8 meters. This is easy. Then I ask you for the speed. The speed is F lambda. Let's see. The speed is F lambda, and so F is, let's see, I said F is 1.5 and lambda is 8. We got 12. 12 meters per second. So let me think here. Oh, I'm going to ask another question and let you think about it for a second. Actually, I'm going to let you think about it. I'm going to run and get a piece of demo equipment right quick while you think about my next question. Here's my next question. What if they get all excited and they start shaking it more frequently? They start shaking it and they make it look like this. Oh my goodness, they up and make a fourth harmonic. The fourth harmonic, they change to the fourth harmonic. What I want you to do while I run and get something is I want you to very quickly calculate everything over again. Okay, hang on. I'm back. Okay, so calculate it all over again. The question becomes, what changes, what stays the same? And this is crucial, and people miss this problem sometimes because of this, but I'll be nice and clear about it. The thing is, you got to figure out what gives. What's going to change? Obviously, the wavelength changes. You can see the wavelength changes. The new wavelength in this picture, in the red picture, is clearly half of 12. So the wavelength has changed to 6 meters. That's easy. What about the frequency, the period, and the speed? You see, you might imagine, for example, that this information here remains true. After all, I didn't say it changed. I didn't tell you it changed. So maybe that stays the same. And then you figure out other stuff and the speed's different. Maybe. But I got to tell you something. I didn't get to show you this, but so I'm just going to kind of tell you. The speed of a wave does not depend, at least generally, on how quickly you're shaking the medium. Let me give you an example. Suppose I'm letting you leave the room. You're sick of class, and you're just itching to get out of there, but I'm just really a control freak, and I only let people out of the room when I want them to leave, and they take off running when I leave, or when I let them. So what I do here is I let you, what if I let people leave once every second, and you take off running at, say, 5 meters per second? Then every person's they're all going to be 5 meters apart, right? What if I let you go more often? What if I let you go every half a second? Are you going to still be 5 meters apart? No, because you're going to run the same speed, and I'm just going to release you more frequently. You'll be closer together. The frequency with which you do something doesn't affect how fast it moves through the medium. How often I shake a spring doesn't affect the speed of the pulses. What does? Oh, I'll tell you what does. The spring itself. You get a different spring, like a big old heavy spring, real heavy spring, and you hold it the same tension and everything. those waves aren't going to go very fast because it's so hard to wiggle. It's all sluggish and the waves go slow. Nice light spring, they go fast. What if you tighten it up? If you tighten up the thing, then maybe they go faster. I'm not sure you know that, but if I had the spring here, I'll do have the spring appliance, but it's on the table. But anyway, if I tighten up the spring, you'd see the waves go faster. Here's the thing. In this problem, I'm going to point out it is the same spring stretched to the same length. Therefore, the thing that stays the same is the speed. The speed is stuck at 12 meters a second because I didn't go get another spring and I didn't change the nature of the spring I'm using. So that stays stuck at 12 meters per second. That means something else gives. That means I can figure out F. F is going to be, I guess it's going to be V over lambda. And that's going to be 12 over my new, it's that. Oh, now the frequency is 2 hertz. It was 1.5 hertz, now it's 2. Now instead of shaking it 1.5 times a second, they're shaking it 2 times a second. What about the period? Well, it's 1 over the frequency. It now becomes half a second, 0.5 seconds. They're having to shake it in less time. I mean, do they shake it more often, more frequently? So you'd see them going at it like crazy there. It's the same spring, same length. They're just shaking it more frequently. So I've just given you a prototype of how you would solve a problem that I'm bound to give you for homework. Now what I want to be able to do is shake a spring for you. But let's see here. Uh-oh, you heard it. So what I want to do is use this for demo. I usually just sit with it in my lap. So I put the strap on this time. See? Okay, so what I'll do is, see, this is a spring. Well, it's a string. It's a metal string. And it vibrates. And it vibrates in what harmonic? This is going to be interesting to see what the camera shows. I'm not sure about the frame rate on this thing. Let's see what happens. You probably can't see that real well. I don't know. It's currently vibrating in the first harmonic. It's doing this. Like that. Because I plucked it in the middle. And so it makes one big old antinote in the middle. It's first harmonic. Now this string, I'm also going to pluck it in the middle. And it also vibrates in the first harmonic, but they sound so different. Why do they sound different? Well, what's the same is the wavelength. The wavelength of each of those things is twice the length of the string because it's the first harmonic I'm doing. But anyway, it's twice the length of the string. Now, so they have the same wavelength, and yet they had different frequencies. I don't know if you know this yet, but you're going to know it right now. Frequency, the physical concept of frequency, is connected very, very closely with the human perception of pitch.
High frequency.
Low frequency. See? Different pitches. This is a low frequency, relatively speaking. This is a high one. Why is it different? Because the speed of propagation along the string is different, because this one's easy to wiggle. This is a nice little thin light string, which has real fast waves on it. Waves go real fast on that thing. Waves on this don't go so fast because it's all massive and harder to shake, and they go slower. What's the same about them is the tension. They're under about the same tension. Guitar strings are designed so that you have them all under the same tension, so that you can, nicely strum your thumb across them, and it's not like some of them are hard to pull and others are easy. You could do that. You can tune it differently. It's kind of that way, but they design it to be that way. Now, you also can change the tension if you want to. That's what these things do. See? I was changing the tension and therefore changing the speed. And since I was changing the speed and keeping the wavelength constant, it was twice that, I was changing the frequency. I got to do a little thing that I got to explain some other time. Oh, I hear beats. Hear less frequent beats. Now it's back in tune. Now let me show you some other harmonics here. So this was the first harmonic. How would you get a second harmonic? A second harmonic is this kind with a note in the middle because it's got anti-note here, anti-note here. The trick is you got to put a note in the middle. I'm going to put one right there with this finger. Listen to the difference. Listen to this. This is the first harmonic, and this is the second harmonic. Ooh. I can do a third harmonic. See, if I put my finger here, you can see where I'm putting it. I'm putting it a third of the way down the string. I'm planting a note right here, and if a note's going to be here, a note's going to be here, and it's split up into 3 chunks, and it's the third harmonic, and it's higher. Listen to that series of notes. Maybe one more. Harmonics on a guitar string. So anyway, harmonics sound good, you know. I'll play something else another time, maybe. I'll probably post something. But anyway, so this is some stuff about standing waves, and why do we like standing waves? Lots of reasons, but one reason is because that's how musical instruments are made. Musical instruments are based on the whole idea of standing waves. String instruments, also wind instruments, the same kind of a thing, where you have a column of vibrating air and it has harmonics. And the nice thing about these harmonics, they really sound good together, and that's what determines a musical scale, something with a lot of notes that are harmonics of other notes, and they all work well together. So anyway, I made my point about how long is this video? I've gone on 37 minutes almost. I guess I'll stop for the time being and post more about waves later. There'll probably be plenty more coming because this is good stuff. So talk to you later. Bye.